Welcome to our discussion on interest. Let's start with simple interest, which is really just a learning tool. Simple interest doesn't exist in the real world. So you probably already know all these things. Interest is the amount of money paid for, borrowing money. Principal is that amount that is borrowed, sometimes called the present value. And then, of course, when we talk about the interest as a percentage of the principal, then we now talk about that as being the interest rate. Time is just the length of time that that money is borrowed. And this is the biggie, this is the important thing. Unless told otherwise, always assume time is stated in years, right? So in all of our formulas that we're going to use to compute things, time is always in years. So if you're going to borrow something for 6 months, you're going to have to put in zero point 0.5 for time, right? So here's our formula for basic simple interest, which again is only for learning purposes. There's really, unless you're borrowing money from a relative, you're never going to see simple interest, right? All lending institutions always use regular compounded interest. But in any case, these letters pretty much remain the same throughout all of our formulas. I is always going to be the amount of interest. P is always going to be your principal or the present value, the lump sum of money that's being borrowed or lent. R is always the annual, that's important, annual percent rate or annual interest rate. And then T is always in times. Oh, and R, by the way, is always as a decimal. So if you're paying 5% interest, you would put 0.05 for R. Okay? So let's look at a simple example. Suppose you have 20 cents, suppose you save 20 cents per day, but only for a year. At the end of the year, you would have saved $73. If you then put that money into a savings account that gives you 3.5% interest, how much interest will the bank pay you after 1 year? Well, our present value is 73. Our interest rate is 3.5% or 0.035, right? Always as a decimal. And then the time, always in years, is just going to be 1. Very simply, you plug everything into its bits and pieces, throw it into the calculator, round to the nearest penny, right? You're always going to round these answers. Anytime you're dealing with money, you always round to the nearest cent. And you'd make $2.56 in interest, and you'd be rich beyond your wildest dreams, right? Okay, how about how much interest will you earn in 3 years with that same $73 deposit? Well, now you just do PRT, or T is 3, and you see that when you round that, you get $7.67, which is basically 3 times the original amount. But remember, that's simple interest, right? That doesn't really work in the real world, because in year 2 you would be making interest off of the interest, right? Because your balance would no longer be 73. It'd be 73 plus that $2 and whatnot, so you'd be a little over $75. Okay, well, the future value is always how much you will have at the end of a certain amount of time, and we let that be A for amounts. So if you want to go, why is it A for future value, not F? Because it's the amount you will have after so much time is how I tell my students to remember it. And that amount is always the principal plus interest. So here's another simple example. There's a car that's selling for $12,436. It's advertised at $290 per month for 5 years. You could figure out, well, how much interest are you paying on that loan, right? Very, very simply, you just go, well, 290 times the number of payments, which is times 12, because you're paying per month, times 5, so there's 60 total payments, and 290 times 60 is 17,400. That's how much money you're actually going to pay for that car. And if you subtract, right, the interest is just the amount you pay minus the principal, you can see that in essence you're paying almost $5,000 in interest. That's pretty heavy, right? Okay, interest for part of a year. Remember, T is always as a year. And to make the math easier, oftentimes these calculations are done with 360 as being 360 days in the year instead of 365, because technically there aren't even 365 days in a year. There's 365.25, right? Because every 4 years we have a leap year. So there's really arguments as to which one we should use. Should we use 360, 365, 365.25, blah, 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 blah. Usually, just to make the math easier, we're going to use 360. So unless told otherwise, just plan to use 360. So here we go. Suppose you borrow $1,200 on March 25th at 21% simple interest. How much interest accrues by September 15th? So you got to count up how many days there are, from March 25th to September 15th, and you get 174 days. And then you got to figure out, okay, well, I'm paying 21% simple interest, but that 21% is for the year. I'm not borrowing it for a year. I'm only borrowing it for a portion of the year, i.e., 174 out of those total days. And so we have a principal of 1200. We have our interest rate of 0.21, that's 21%, and we have our time as number of days divided by 360. Right? We're going to do 360 instead of 365. And when we stick all of those things into the formula, and you'll notice that I left time as a fraction. You guys got calculators. Leave it as a fraction. So when you type all this stuff in, because if you do 174 divided by 360, you're going to get this really ugly decimal. And then if you round that decimal and then plug that back in and multiply by 0.21 and 1200, you've double rounded, right? And you're compounding your errors. You don't want to do that. You want to leave everything as precise as possible and only round at the end. So it's much better to leave it like this. Use your calculator, right? 1200 times 0.21 times 174 divided by 360, enter, and you get 121.8, and you can see that the amount of interest you would pay for that, a little bit more than half of a year is $121.80. Okay? So then, of course, the amount that you would have to pay back at the end of the, total loan would be principal plus interest, or $1321.80. Okay? Simple. So it's easy if we look at this that we can kind of come up with a formula for future value based on present value plus interest, so P plus I, and then we realize, hey, the interest is just principal times rate times time, and then we can factor out the P, the principal, and get principal times 1 plus RT, and that becomes our basic formula for simple interest. And again, not really used in the real world, most often just as a teaching tool. But if you get the idea of how this formula works, it will help you see why the other formulas are what they are. Okay, so now we can find the future value of something a little quicker. We don't have to do this in bits and pieces. We don't have to calculate interest and then add it back. If we just use this formula, we can kind of do it all in one piece. So we've got 10,000. We're getting 1 3/4 simple interest. They want to know what's the future value in 5 years. So we just plug everything in, right? P is 10,000. R is 0.0175 because that's 1 3/4 as a decimal. Our time is 5. We throw it into this formula, put in all the numbers, slap it into your calculator, and in 5 years you'll have 10,875, and you can see that you made a total of $875 in 5 years. All right, so let's suppose you, instead of knowing how much money you have at the end of so many years, you need to have a given amount of money after a certain amount of time. And that's kind of a more realistic, real world question. Because if you want to retire, let's say you figured out, okay, if I don't have a home loan, I've paid off my home, I've paid off my car, I just need $4,000 a month for food and utilities and just living expenses. So how much money do I have to have in my retirement account by the time I want to retire, so that each month I can take out $4,000 and then still have that same amount, right? Because if I have, let's say I have $1 million, and in 1 month that earns me $4,000. If I take that $4,000 out, I still have $1 million, right? And then at the end of the next month, I have $1 million and 4,000. I take that 4,000, and I can basically do that until I die, and then leave the $1 million to somebody or something, right? So that's the idea, is to be able to perpetually live off of just the interest. And if you found some retirement fund that pays you 8% simple interest, and you figured you needed 4,000 to survive, then the question is, how much money do we need in order to pull this off, in order to be able to get this 4,000 each month? So we know interest is 4,000. We know our interest rate is 0.08, and we know our time is 1 month, which is 1/12 of a year. Now we plug that into the formula and solve for what we don't know. We don't know principal. So now all you have to do is get rid of the fraction, right? So we can multiply both sides by 12, then divide by 0.08 to solve for P, and it tells us we need $600,000. So if we can somehow save up $600,000, we'll be able to retire and get that $4,000 per month to live off of. But again, that would be with simple interest, and that's really not how the world works. So let's talk about compounding interest, which is the more real world thing. So let's compare simple and compound interest so you can see how it works differently. With a $10,000 deposit at 1.95% for 3 years, let's look at what happens. If there's our principal, there's our interest, here's our time, stick it into our simple interest calculation, right? And we go, all right, after 3 years, we've got $10,585. Simple and easy. Now, let's assume that the interest is compounded annually, which also really doesn't happen a lot in the real world. Interest is usually compounded pretty quickly. Monthly is usually the slowest. Daily usually happens more often than monthly, and usually most things are compounded continuously. Even though interest is paid out every month, let's say on a savings account or something in a bank, so it feels like it's being compounded monthly. In actuality, it's probably being compounded continuously. They just pay it out every month because it takes a whole month before you make a few dollars. So it doesn't make sense to give you half of a penny each day kind of thing. Okay, so if things are compounded annually, at the end of the year, you have your money plus your interest. And so the following year, that new amount, it becomes your principal. And so your interest is now based on the amount plus the principal. So instead of just calculating your interest for 3 years, you're basically calculating it 3 times for each year. So we'll start off with our first year, right? T equals 1, and use our simple formula, and we get 10,195. But now that becomes our principal for year 2. So year 2, again, we're doing it for 1 year, right? So we're using the same P times 1 plus R times T, but remember T is just 1. But now our principal is the 10,195. Everything else is still the same. And at the end of 2 years, we now have that much. So we put that in to our calculations for the third year, and we get our final amount. Now you'll notice that we always took the principal and multiplied it by 1 plus r, right? So you multiply by 1 plus r times 1 plus r times 1 plus r, and that's 1 plus r cubed, and you can see where we're going to start to get this formula for compound interest. You can also see that we did make more money when we compounded, which makes sense because instead of just that 1.95% on the same amount, we were getting 1.95% for a growing amount each year. Now, like I said, we normally compute more frequently than per year. So when you see words like semi-annually, that means twice a year, quarterly 4 times a year, monthly 12 times a year, and daily, just to make the math easier, we're going to go ahead and say that that's 360 times a year. Depends. Some people like to use 365. We're going to use 360. So let's expand that and see that when we look at these different compoundings, that means that we have to compound multiple times in each year. When we're doing annual compounding, we just do this once per year, right, where T is the number of years. But if we're compounding semi-annually every 6 months, then we're multiplying by this 1 plus r times 1/2, but then we have to do it twice per year, right? So 2 times however many years. And if we're doing this quarterly, then it's 4 times per year, and then monthly, 12 times per year, and so on and so forth. So you can start to see a pattern emerge with these things. And when we kind of generalize it, where n is now the number of compounds in a year, we get our first real formula, meaning a formula that would actually apply in the real world for future value, that it's P times 1 plus R over N to the NT, right? So if we're doing quarterly, N is 4, monthly, N is 12, daily, N is 360, or depending on the class you're taking, N might be 365, all right? So we can contrast simple and compound interest very easily use the simple interest formula if interest is withdrawn from the amount in the account, i.e., if you earn interest and then that interest is taken away so that the next time interest is calculated, your principal doesn't get bigger, then you would use the simple interest formula. However, if the interest stays in the account and accrues and your principal basically goes up and up and up, then you would use the compound interest formula. So the only time you would ever think about using the simple interest formula is if you were in that first scenario where you had the 600,000 and every month you took 4,000 out of the bank, because at the end of the month you earned 4,000 interest, you withdraw that 4,000, you spend it, and so now for the next month it's still calculating interest on 600,000 only because that extra 4,000 was taken out, right? So that would be a simple interest, calculating kind of thing. So back to our letters, you can see that everything is still the same. P is still present value, R is still interest rate, A is still future value, T is still time in years. Now we have N being the number of compounding periods each year, i.e. the number of times you're going to compound interest each year. And then M is a new one. We call that our periodic payment. And this is usually monthly, which is why we use M. Okay, so M doesn't come up a lot, but just keep that in mind that that's your periodic payment. So let's run through some examples really quick of finding the future value when we invest $1,000 for 10 years at 8% interest. We're going to compound it a bunch of different ways. So if we compound it annually, that's what we get. If we compound it biannually, that's what we get, right? Quarterly and daily. And look at the difference in the monies, right? They all go up. Because remember, we invested the same amount, $1,000 for the same amount of time at the same interest rate. The only thing that changed was how often interest was compounded. And you can see that it makes a substantial difference, right? From yearly to daily is a pretty big difference. And that's why banks, of course, compound continuously, because that maximizes the amount of money they make, i.e. maximizes the amount of money you own, which brings us to continuous compounding. So let's figure out how and where this formula comes from. Suppose $1 is invested at 100% interest for 1 year, compounded at different intervals. We've got our normal little formula, right? 1 plus 1 over n to the n, and t is 1, so that's why the t is gone. You can see that if we compound annually, semi-annually, quarterly, monthly, daily, the amounts keep going up, right? Up to 271. And in fact, if we now start compounding more frequently, so every hour, every minute, that's where those numbers come from. And then even more than that, so you're talking about every second, every half of a second. Look at the pattern with the numbers. Can you see how the digits all seem to they're going towards something. They're trending towards something. And that number that it's trending towards is an actual number. We call it E for Euler's number. It's also the natural base. And it's one of those weird irrational numbers. Probably the only irrational number that you're already familiar with is pi, right? Because pi is 3.14159, blah, 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 blah. And that thing, the decimal expansion goes on forever. It never repeats. It has no pattern. It doesn't stop. And that's basically the definition of an irrational number. Well, E is the same thing. It doesn't have a pattern, right? It never stops. It goes on forever. And so we just give it this name because we can't just keep writing this number with a billion decimals after it. So basically, E is defined by this formula. If you take this and then let n increase without bound, i.e. let n get as big as you want. We basically say we take the limit as n goes to infinity. And as n goes to infinity, when you take 1 divided by a really super big number, you can see that this tends to get to 0, right? And then this gets really super big. That ends up being E. And then if we plug that into the formula, this is where we get our continuous compounding formula, that the amount is the principal times E, that weird number that we just kind of created, raised to the power of R times T. And you can see where this formula comes from if you do this simple substitution, where 1 over m equals R over n. And so therefore, if you cross multiply, right, you get N equals MR. It'll make more sense on the next slide. So we have our standard formula for compound interest, right? That's what this is. Now we do our substitution where R over N becomes 1 over M, and then remember N was equal to MR. So all that happened here is we did that simple substitution. Now when you look at this, when you have something raised to a power, you can always cut that apart and make it a power and then another power, right? If you raise to a power and then raise to a power again, those two powers get multiplied, right? So this is M times RT. Well, we can also use that property in reverse and say, okay, well, it's raised to the power of M and then it's raised to the power of RT. But look at 1 plus 1 over m to the m. That is that formula. We said anything that was of the form 1 plus 1 over n, n is in Nancy, raised to the n, that is e. As e gets, as n goes to infinity. Well, here we just have m's instead of n's, but it's the same pattern, right? It's the same thing. So that is e. So by substitution, this thing becomes e, and it's e raised to the RT, and that's where the formula comes from. I'm sure most of you could not care about that any less than you already do, but in case you want to know where it comes from, that's where it comes from. Okay, another example where we can compound continuously, and really it's just a matter of plugging everything in, throwing it into your calculator, and doing the math. Now again, when we talk about 240 days compounded continuously, because we're now compounding continuously, we're going to use 365 because we want to get as close to a real year as possible. So if it's continuous compounding, you can assume 365. Otherwise, you can assume 360 for daily. This is, an interesting example. You're not going to get a lot of these. Usually you're going to use continuous compounding for multiple years rather than a piece of a year, right? That example, we were doing it for 240 days. It's usually going to be continuous compounding for 5 years, and then that's easy. You don't have to worry about it. You just put in 5 for t, and you're good to go. Okay, what about inflation? Well, we can't talk about compound interest without talking about inflation, because that's basically what inflation is. It says how much do things go up over so many years. And for instance, in 1980, the inflation rate was over 14%, which is pretty huge. And in 2015, it was less than 1.25%, which is pretty small. So that means the cost of things can go up by quite different degrees. So you would use this idea of how much is something, like how much more is a new car going to cost in 20 years? How much more is a loaf of bread going to cost in 20 years? How much more is a house going to cost in 20 years? And if everything went up by 10%, but your salary didn't go up by 10%, in 20 years, you wouldn't be able to afford the things you can afford today. And that's kind of the idea of inflation, is if we know things go up by 6% roughly, right, on average, then we need to make sure our salaries go up by 6% just so we can continue to afford the things that we afford today. With that in mind, if you make $55,000 a year now, what should you expect your salary to be in 20 years if we assume inflation will continue at a constant rate of 6%? Now, inflation never goes up at a constant rate. It fluctuates. Some years it goes up more than others. But if we look back over the last 20 years, we can see that on average it went up 6 per year. So that's a pretty good kind of guess for what we think will happen in the next 20 years. So that's why we're using 6%. It's just our best guess of what we think would happen. So we've got our principal. We've got our interest rate, right, of 6%. We've got our time of 20. We're going to do continuous compounding, right, because that's the way the world works. Plug everything into our calculator. And if we rounded to the nearest $1,000, you would have to make $183,000, which seems like a whole heck of a lot than 55, and it is, in 20 years, just to be able to afford the same thing, right? So just be able to put food on the table and pay your bills the way you are now, that's what you'd need. Now, I'm going to give you all these present formulas, but just know that you really don't need a lot of these because they're just formulas we've already seen that have been algebraically solved for another letter. So it's not really necessary. Because remember, the original formula was just A equals P times that stuff, right? So if we go here and remind ourselves of what the other formula was. It was A equals P times 1 plus R over N. It's the NT, right? So if you wanted to solve for P, you would just divide both sides by that, and that's where you get A divided by that. Well, when you divide by something to a power, it's the same thing as multiplying something times its negative power. So that's all that's happening here is we're using some rules of exponents. So now if you want to take a trip in 5 years and you decide you need 5,000, you want to know how much money you need to set aside so that you can do that if the bank is going to pay you 6% compounded quarterly. So our P is unknown, but our A is given, right? The A is how much we want to have. We want to have 5,000. We need to know how much we need to invest now. Our interest rate is known at 6%. Our T is 5, and our N is 4 because it's compounding things quarterly. So all we got to do is plug everything into that formula that we just derived, slap it into our calculator, and we basically need to deposit $3,712.35 into our account today so that we can afford that trip when we want to go. And that is it, my friends, right? So that is everything we need to know about interest.